Happy New Year and welcome to our next unit. We're going to be learning about Earth processes, how the world works. We're going to start off learning about the internal structure of the Earth. So, the Earth is not just a big ball of solid rock, as one might think. It actually has an internal structure that is quite intriguing, really. So let's learn a little bit about it. The Earth is actually comprised of four fundamental layers. I mean, you could subdivide some of them, but for the most part, we say, look, there's four layers of the Earth. Starting at the surface here, the part we live on is called the crust, and it's very thin, kind of like the shell of an egg compared to the interior of the Earth. The main part of the Earth, the main interior part, is known as the mantle. Below that, we have a liquid outer core, and inside that, we have a solid inner core. And we'll look at each of these in turn. Okay, so let's work from the inside out. Okay, might as well. So the inner core of the Earth is made out of solid iron and nickel. Uh, and it's this very dense, heavy ball of metal that's basically the size of the moon. And it's really, really hot. So 6,000 degrees Celsius. So just that's about the same temperature as the surface of the sun. So if you could go to the center of the Earth and look at it, it'd be like looking at the sun. Now, the interior of the sun is considerably hotter, like 10 million degrees. But the surface of the sun, the part we see with our eyes, the white part we see, that is basically the same temperature as the core of the Earth. Now, why is it so hot in there? We know it is, and that was a matter of some debate for quite a while in science until someone finally realized what the deal is. Turns out that when the world first formed, it was all liquid, and the more dense materials were drawn inward by gravity, and so all the larger, more dense atoms tend to be congregated in the center of it. And again, it's mostly iron, and that just has to do with that's the main heavy metal that stars tend to make as they age. But there's other ones too. And the larger isotopes, which are even more dense than iron, are also located primarily in that core. And even though they're not the main component of it, which is iron and nickel, we still have things like uranium, polonium, radium, basically uh, uh, isotopes of elements that are greater than 84. So, once you get to 84 protons in a nucleus, you just can't hold that nucleus together, and it tends to decay or break apart by giving off radioactive particles, particle radiation, in this case, usually alpha rays and beta rays, and also giving off a lot of energy, which then gets converted to heat. So the reason it's hot inside the Earth is because of radioactive decay. So in a sense, we have a nuclear powered Earth. It's not a nuclear reaction. It's just decay products is what keeps it so hot inside. Now the outer core of the Earth is comprised of the same. It's essentially from a material perspective, it's the same composition as the core of the Earth, the inner core, except it's liquid instead of solid. And that has to do with the fact that there's less pressure because it's not as deep. So by dropping the pressure a little bit, the same materials at essentially the same temperature, a little bit cooler, but with less pressure, they behave as a liquid rather than as a solid. Now, here's what's really kind of interesting and important here. The outside of the world spins basically on its axis once every 24 hours, and that includes the mantle moves with it, okay? So it goes through 360 degrees every 24 hours. But the inner core is traveling much faster. Just think about if you've studied physics, you could talk about conservation of angular momentum as like if you've seen what do you call it, a ballerina or an ice skater, as they draw their arms in, they spin faster. And so basically, the inner core, because it has fallen essentially inwards, it spins faster. And so the difference between the spin of the outer part of the Earth and the inner core, with a liquid outer core sort of trapped in between the two. And so what it essentially does is it's like a blender, it stirs it up. And so what that does is it produces these vortices, kind of like when you pass an ore through water. So you've got these vortices, these swirls in the liquid outer core. Well, this material is so hot that a lot of them, and this is metal, so a lot of them have lost their electrons and they're charged. And so when you swirl these charged particles, basically it's what we call a dynamo. You've essentially made a magnetic field. So you have like an electromagnet. So the interior of the Earth acts like this big electromagnet, and that produces the world's magnetic field. So if at some point in the future, far, far future, the outer core will freeze. And when it does, we'll no longer have this pronounced magnetic field. We'll just have a very, very weak one, that's a residual one that's left over. But as long as we have those swirls in the liquid, we have a very strong magnetic field, which is really important because it protects us from cosmic radiation. In fact, one of the big concerns about sending someone to Mars, like manned missions to Mars, is it's probably going to be a death sentence because once you get outside of Earth's magnetic field, which extends considerably into space, uh, when you get outside of that, you are basically unprotected from these rays that are streaming out of the sun. But when you're inside the world's magnetic field, it's protecting you, which is really good for us and not so good for these astronauts on their way to Mars, I suppose. Now, what happens to these particles? Well, as these particles come in, they interact with Earth's magnetic field and they're directed towards the North and South Pole. And it's worth noting that the North Pole of the Earth, the axis of rotation, is not exactly the same as the magnetic field. As a matter of fact, the North magnetic pole and South magnetic pole, they drift. In the course of my life, they've drifted hundreds and hundreds, if not thousands of kilometers. In fact, we'll talk in another screencast. There's very compelling evidence. In fact, we know for a fact that the magnetic pole sometimes flips, and the like if you had a compass when this happened, it would swing around and point the opposite way. Well, anyway, these magnetic field lines extend out into space, and when charged particles from the sun, which we call the solar wind, like there's like electrons and protons and things like that streaming out of the sun, when they interact with these magnetic fields, because they have an electric charge, they respond to magnetic fields, and they're then channeled towards the poles. And as they come into the Earth's upper atmosphere and enter the thermosphere, they encounter molecules there, and they tend to slow down and give off energy. These beautiful light displays known as the auroras. So the aurora borealis over, say, Greenland, and the aurora australis over Antarctica. All right, now let's talk about the mantle. So the mantle is the main part of Earth's interior. Is the largest volume of the Earth is the mantle, and it is from a compositional standpoint is distinctly different from the inner and outer core. The inner and outer core are essentially composed of the same thing, but the mantle is not. Okay, so the mantle has significantly more silicon and significantly less iron and nickel in it. Now it still has some, right? But the main thing is it has a lot more silicate, which is silicon and oxygen, which SiO2. It's what sand is made out of. But I don't want you to get the wrong idea. It's not like the interior of the mantle is not like sand, but it has a lot of that same mineral component in it. But anyway, so the mantle is large. It's like 84% of the volume of the Earth. And here's the main thing you need to know about the mantle, apart from the fact that it is chemically different from the core. And that is that it behaves in a semi-solid way. So I guess the best way to describe it is it's like a solid, but it's capable of flow. So it's kind of like gum or cement, maybe. So we know that there are convection currents that occur, and these are going to be very important in understanding the dynamics that govern the shape of the Earth's surface. So we know that hot material rises up in the mantle and the cold mantle material sinks down. So we have these very slow moving convection currents inside Earth's mantle. And that's the main thing you need to know about the mantle. In the mantle is very hot near the core and it's cold at the surface. So it's probably like the top of the outer core, maybe like say, I don't know, 5,000 degrees. I go back and look, I don't remember. 4,000 or 5,000 degrees, and the surface is about 12 degrees. So what happens is hot material moves up, it cools off, and it sinks down, and that's the main thing you need to know about the mantle. Now, the crust of the Earth is the part that we live on. So the crust is just that very, very skinny top layer. It's like it's like the skin on not even like a skin on an orange. It's even thinner than that. It's more like a shell on an egg. It's very thin compared to the rest of the Earth, right? And it's the only part of the Earth that behaves the way we think of rock behaving, right? As solid rock, okay? And if you hit it, it breaks, okay? It's the only part of the Earth that acts like that. And it extends down at most maybe 70 kilometers over the continents and maybe 7 kilometers over the oceans. We'll talk about that in a minute. But the thing is, it's primarily made out of silicon dioxide. And there's two types of crust. So if you look, let's see, here's a pie chart. You see like silicon and oxygen make up the bulk of it. And then we have things like calcium, sodium, potassium, magnesium, things like that. They make up the rest of it. But but it's primarily made of silicon and oxygen. Now, the crust is different in thickness depending on where you are. So, if we go to the continental crust where you and I live, what we find is that a couple things. One is the material here contains less iron and magnesium and more silicon and oxygen, so it's less dense. So what probably happened is when the Earth first formed, it was all liquid, and this part of it just floated on top, like fat floating on top of the soup, and then it all froze. Okay, so this part is thicker and less dense. Now the oceanic crust tends to be thinner, like maybe 7 kilometers thick, uh, and it is which is shown here in orange, and it's considerably denser. Now, when we come now, the upper part of the mantle, which is here, okay, uh, it when we get close to the surface, it becomes brittle like a rock. So when we get to that part here, litho means rock. So the lithosphere is the crust and the upper part of the mantle. And so this is the region in which we would expect to find rocks behaving the way you think of rocks would behave. Well, how do we know what the Earth is like inside? Have we sent people down there? Do we have like earthonauts who went down there? And the answer is no, we don't. And we certainly didn't find out by drilling. Okay, so well, we know the world is hot inside. Like there's mines in Africa, gold mines that are so deep that people can only stay down for like less than a half hour before they have to come back up. It's so hot. They've tried to drill down as deep as they can. They haven't even gotten as far as the mantle. What we find is we get down about 12 kilometers, and the equipment begins to melt because the temperature gets up around 180 degrees so Celsius. So like, how do we know what the internal structure of the Earth is? And the answer comes oddly from earthquake data. Now we're gonna have a lot more to say about earthquakes in a later lesson, but let's just talk about it right now. So earthquakes produce two types of waves, and again, more on this later. But the two main types of waves that an earthquake produces are called P waves, which are like sound waves, where material moves back and forth. And then there's S waves, or shear waves, where material moves side to side, like when you shake a rope. Okay, so these P waves are like sound waves, and if you've ever been underwater, that you can hear underwater. If you go underwater and somebody whacks two rocks together, or there's a boat, you hear it. P waves, which are pressure waves, push and pull waves, longitudinal waves, whatever you want to call them, they travel through liquids. They travel fastest through solids, slower through liquids, slower through gases. All right, but they travel through all of those. S waves, on the other hand, do not. S waves, just like if I shake a rope is solid, right? They'll travel through solids, but they don't travel through liquids. If you took your hand in a pool and you went like this, underwater, you wouldn't get the water molecules to do that. You can get them to go back and forth like a P wave, but you can't get them to do, the shearing doesn't happen in fluids, in liquids or gases. So P waves happen in solids, liquids, and gases. S waves only happen in solids. And because of this, we're able to figure out what the interior structure of the Earth is. Now, it's far more complex than what I'm talking about. You have to understand about the role of density and fluidity on the speed with which these waves travel and what that does to a concept called refraction. However, let's just look at this here. The idea is this: if an earthquake happens anywhere in the world, these waves are going to move out across the world at a certain speed. And what we find is that monitoring stations, which are all over the planet, will pick up this earthquake. The farther away they are, the longer that will take to get to them. But what we find is you get to a certain point, and beyond that, you don't pick up any signal from that earthquake. There's what we call a shadow zone. And the shadow zone extends 103 degrees on either side of that point that is opposite of the earthquake. Okay? So you get this 206-degree shadow zone. And so scientists, based on that, can say, well, we know why that is. S waves can't travel through liquids. So based on this distribution of waves, they're able to say this is how big the liquid part of the core must be. So the way we know the core, the outer core is liquid, is because of the shadow zone where those S waves could not pass through it because they don't travel through liquids. But then how do we know the middle of it is solid? Well, then there's P waves. P waves, as I said, travel faster, like all sound waves, through solids than they do through liquids. Now, this diagram is a little bit, like I say, it's complex, and it has to do with a property called uh, um, refraction, which is the bending of waves as they change speed. But we won't get into that, okay? But I will just point out this. If we just look down here, directly opposite of this, okay, so where the waves aren't bending, so to their, okay, refraction doesn't happen when things come in perpendicular to a surface. What happens is, if I look at the point opposite the world where that earthquake happened, if this was all liquid, well, these waves travel slower through liquids. So we'd expect the arrival time to be, let's just let's make it up. We'll say we expect it to arrive maybe 10 minutes after the earthquake happened here. Let's just make up a number, okay? But we find is instead of arriving 10 minutes later, it arrives like 8.5 minutes later. It arrives sooner. Why would that be? Well, at some point, it must have been traveling faster than it would if it was liquid. And based on that arrival time, they can determine that there must be solid material in there, and they can actually determine the size of that solid. And that's how we know that the inner core is about the size of the moon, and that it's actually solid in there. Okay, so that's the internal structure of the Earth. I don't think I have anything more here. No, that's it. Thanks for listening, and I'll have another one for you to listen to